Okay, so let's try an example of maybe using Green's theorem if we can. So I would like to integrate over a curve C a vector field f dr, where the vector field f is given by x to the fourth comma xy, and where my curve is the triangle formed by 0, 0, 1, 0, and 0, 1, and it's oriented, which way is this?
Counterclockwise.
Counterclockwise. Cool. Okay, so before I can apply Green's, what do I need to check?
Let's see. That's positively oriented, piecewise smooth.
Okay, so for Green's, you need positively oriented, check. Piecewise smooth. How many pieces does this, how many smooth pieces is this? 3. Finitely many smooth pieces. Cool. What else? Piecewise smooth.
Closed.
Closed. Is that a closed curve?
Yes.
Yep, makes a loop. And simple. And is this thing a simple curve?
Yep.
Yep. Cool. Check. You guys cool with this?
So then
Cool. I can apply Green's theorem. What the hell? What do I apply Green's theorem to?
is let P and Q have constant properties.
Okay, so let me write down Green's theorem maybe. So Green's theorem tells me that the integral over C of P dx plus Q dy is the double integral over D of the partial of Q with respect to
X.
minus the partial of P with respect to Y, D.
Wait a second. Yes, doesn't matter.
Or D.
The area. Yeah, and so it's important that the Q, right, the Y component of the vector field ends up getting X differentiated, and the X component of the vector field gets Y differentiated. And you subtract those in this order as Q dx minus P dy. If you subtract them in the other order, what are you assuming about your curve? Yeah, that's clockwise oriented.
So would those be?
You see that?
If this is if P and Q are components of a gradient, then that would be Fyx and Fxy.
Yeah, so if my vector field F were a gradient of something, right? You guys see that?
Oh.
If it were path independent, what would the integral over a closed loop be? 0. Also, if this were the gradient of something, this thing would be Fy with respect to X, and this guy would be Fx with respect to Y. Clairaut's theorem would tell me that this chunk is then 0. So that's actually kind of how you would show that, right? You kind of with me on that? Okay, so is this thing the gradient of something?
No, I mean, no, it's not.
Probably not. It would have to be x to the 5th over 5 from this chunk, right? Plus a constant with respect to y, right? Or a constant of y. And this guy would have to be
1/2 xy squared.
1/2 xy squared.
Which means a
Oh,
1/2
which doesn't
y
match
squared.
either of the pieces that I had over here, so this isn't the gradient of something. You guys cool with that? You should spend a second and check. It'd make your life easier. How do I apply Green's theorem to this thing? Like, what do you need?
So we need a P and Q that have.
Okay, I got a curve. Don't bother parameterizing it. Because the point of this is that this saves you the trouble of parameterizing free curves. You can turn a parametric curve integral into a area integral. So you need to know, right? I'm going to start with this guy. I'm thinking that's a P dx plus Q dy, right?
Yeah. Okay.
So what are the P and Q in there?
That's P is going to be the X support component.
Yeah, P is the X component, right? That's just X to the 4th. And Q is XY. You guys see that?
Okay.
That's really me thinking about dr as the vector dx comma dy, right? And then doing that dot product to get to that form. Cool that? Okay, so here I am. I'm sitting at, all right, this thing is the integral of x to the fourth dx plus xy dy over that curve C. And so I've identified P and Q. And now how do I rewrite this as a double integral?
That's xy over df partial of x.
Okay, so I need to take the partial with respect to x of xy and subtract the partial with respect to y of x to the fourth. And I need to integrate that in D area, right? By the way, it helps when you guys are doing these if you note which equal sign you used greens at. That really helps me keep track of things if things are going really wrong, which sometimes do. So, what do you get here?
Give me a sec. And then you get to y.
So what's the partial with respect to x of xy?
Y.
Y. And what's the partial with respect to y of x to the fourth?
0.
0. So you need to add up y, the area, right? Okay, so now what? Where's D in this whole jam?
These are whole region.
Yeah, D is the region inside here, right? So this is my region D that I'm talking about.
Oh, so then you just kind of do the whole, do one side and do one thing. Wait.
Wait. Okay, do you want to do this in polar or Cartesian?
Cartesian.
Probably Cartesian, right? Okay. So I'm going to rewrite my double integral of y as d something, right? If you were doing polar, you'd need an r, and then to decide on an r theta order, right? So where does something frickin' range in here? Which one do you want to get rid of first, x or y?
Or if we do y, then x.
I'd do the y first, personally.
Yep.
Okay, so where do the y's range?
From
If I'm in my region D, the y's go from
0 to 1 minus x, or?
Negative x plus 1.
negative x plus 1.
Okay.
Right, this is the line, right? It goes through 1 and then goes with a slope of minus 1. So that's the line y equals 1 minus x. So my y's go from 0 to 1 minus x. And then where do my x's range?
0 to 1.
0 to 1. Very nice, guys.
And
You
so
used
you
to,
have-
do you remember you used to stumble over those?
Yeah. Yeah.
I used to be like, where do the y's go? And you'd all be like, 0 to 1. Where do the x's go? 0 to 1. Guys, it's not a square. You've gotten better, really. It's good. So,
No, it's half a square.
what do you get?
So let's see, the first half. Which is
Like we took a complicated line integral, right? That thing was going to be a pain in the rear. We were going to have to split it into 3 pieces. We were going to have to parameterize each piece. We're going to have to do a shitload of dot products. And now here I am back at like chapter 15 or something, right? This is just double integration. So do it.
It should just be 1/2 times 1 minus x quantity squared.
Okay, so you got the integral from 0 to 1 of y squared over 2 evaluated from
That to
0 to 1 minus x. And so you get 1 minus x squared over 2 minus 0. And you're integrating dx still.
Yeah.
Okay, so then what do you do?
Let me just integrate that.
Just integrate that with what?
I want to simplify it first.
Your brain?
Factor it out.
Yeah.
I would do this. I would pull a 2. You get 1/2 the integral of this crap. And then,
It'd be
yeah, you get a choice. You can either u sub or you could
Just expand it.
Yeah, FOIL. I'm better at foiling than I am at U sub. So I think I got 1 minus 2x plus x squared. Okay, so I get then 1/2 times
X minus x squared.
x minus x squared plus x cubed over 3,
Yes.
evaluated from 0 to 1.
So 1 minus 1
So you
plus
get
1/3. So
1/2, 1 minus 1 is 0, times a third,
1/6.
and then minus 0. So you get, all told, 1/6. Cool?
Barely getting anything out of this.
Yeah, so this, well, this vector field helps you a little bit go around your curve, right?
After a few thousand years, you might get something out of
Yeah.
it.
This
I mean,
is
it depends on what the units are, right? If the units are millions of joules, this isn't bad. If the units are joules, man.
Yeah.
What is this?
Right, but something's something.
It's positive. That's important.
So you're getting some kind of help out of this vector field to go around this little curve. But we didn't actually do a line integral, right?
Nope.
You guys see that? Cool, cool. This is actually kind of neat because this lets me escape from line integrals to area integrals. It also actually lets you go the other way, but the other way is harder.